These are the tough physics problems, and Teacher Gia will help you master them all with selected example explanations. Now let's look at the fourth problem in thermodynamics. This one is not so easy to handle. Of course, if you understand everything, it's still manageable. Let me explain. This type of problem usually appears as a major question, right? In thermodynamics, you often see a Mercury column combined with a masonry structure, and then there's expansion and such. These types of problems are generally big questions among all the thermodynamics calculation problems. There are basically two core things being tested here. In multiple choice questions, they especially like to test the first law of thermodynamics, which we've talked about many times before. Delta U refers to the change in internal energy of a gas, while W and Q represent the work done on the gas by the external environment and the heat supplied to the gas by the external environment, respectively. So, in all analyses, all the forces, work, and heat involved, everything must be considered with respect to the gas. This is the most fundamental issue regarding the first law of thermodynamics, and it's also a common point where people make mistakes. Besides this, another key equation is PV equals nRT. In high school physics, it's called the ideal gas law, right? PV equals CT. In chemistry, it's called the Clapeyron equation. Actually, C is directly proportional to N, so I usually recommend that you just write this formula. If they want to deduct points for your process, just let them. After all, you probably won't get full marks anyway, right? So just write out this formula. With this, your classmates online can help you solve this problem. Of course, if you want to get full marks, you can write it as equals CT and then explain that C is directly proportional to N, right? Okay, then you just do it in 2 steps and you can get all the process points. Now let's take a look at what this question is asking. Inside the tube, a column of mercury with a length h equals 15 centimeters is used to seal off a section of ideal gas that is 30 centimeters long. The external atmospheric pressure is 75 centimeters. So, for this problem, the internal pressure P should be equal to the pressure from the liquid column, which is RHOGH, and then you add the external atmospheric pressure P0. That's the relationship here. But for this problem, later on, you'll definitely lay it flat, right? Of course, you could also turn it upside down. If you slowly rotate it to a horizontal position, then now the pressure from the mercury itself will no longer press down on the gas column, so the gas column will definitely expand, and its pressure will decrease. So if this is P1, then later P2 will actually just be equal to P0. So for this problem, the ideal gas law part is actually very simple. What is P1 equal to? It equals H plus P0, since you're using the height of the mercury column as a substitute. So this, you can write H directly here. So 15 plus 75 means P1 is 90 centimeters of mercury. Centimeters of mercury is a unit of pressure, as you know. P2 equals P0, which is 75 centimeters of mercury, so the pressure has clearly decreased. The tube's good thermal conductivity allows heat to exchange freely with the environment, meaning the internal temperature stays constant and consistent with the outside at all times. So the external temperature must remain unchanged, which means the temperature of the gas inside will always be a constant value, so T doesn't change. Therefore, in this problem, P1V1 equals P2V2. Thus, the ratio of P1 to P2 should be equal to the ratio of V2 to V1. It will also be equal to the ratio of L2 to L1. So from this, I can directly calculate it. The ratio of P1V1 to P2 is 90 to 75. 90 to 75, both are multiples of 15, with 90 being 6 times 15 and 75 being 5 times 15. So the ratio is 6 to 5. Therefore, 6 to 5 is the ratio of these two lengths. So L2 should be 6/5 times L1. L1 is the original length, L, so that's 6/5 multiplied by 30. 30 divided by 5 is 6, and 6 times 6 is 36, so the answer is 36 centimeters. Therefore, after laying it flat, the length of the enclosed gas is 36 centimeters. So for this question, don't worry about anything else. Just use the ideal gas law to reach the conclusion, and you'll see option D is correct. Then you don't even need to check A, B, and C. Let's see why they're wrong. B and C are easy to judge. C says the gas pressure is 60 centimeters of mercury, but that's incorrect. It only becomes 60 after flipping the tube. This means after flipping, the gas column is above the mercury section. And then, below here is atmospheric pressure, right? So it becomes PPR equals P0 minus H, which is 75 minus 15, equaling 60. If you lay it flat, it is 75. If you stand it upright as it is now, it is 75 plus 15. If you flip it upside down, it is 75 minus 15. So you need to sort out these three situations yourself. C is definitely wrong. It should be 75. 2, B is also wrong. During the process of slowly rotating the glass tube to a horizontal position, external work is done on the gas. Throughout this entire process, you can see that the pressure definitely decreases. While the temperature remains unchanged, the pressure decreases. So during the process of laying it flat, the volume must increase, the volume increases. This gas pushes the mercury column outward. The force you apply causes an outward displacement. So this is called the gas doing work on the external environment. So, for this question, option B is definitely wrong. It's the opposite of what's correct. Now, let's look at option A. Whenever you're studying whether a gas releases heat or not, you must use this equation. Don't just rely on your intuition. Your brain isn't that reliable. Delta U equals W plus Q. First of all, since the temperature doesn't change in this problem, delta U is 0. You need to clearly understand that for an ideal gas, there is no molecular potential energy, and intermolecular forces are neglected, so there is only molecular kinetic energy. The molecular kinetic energy is directly proportional to the temperature. If the temperature doesn't change, the kinetic energy doesn't change, and the internal energy doesn't change. So when the temperature doesn't change, 0. Since temperature is constant, PV is also constant. Thus, the sum of W and Q must be 0. The gas is expanding, so it does work on its surroundings. In the first law, W is the work done on the gas. Since the gas expands, the surroundings do negative work, so W is less than 0. If W is negative and their sum is 0, Q must be greater than 0. What does Q greater than 0 mean? It means the heat absorbed by the gas is a positive value. In other words, the surroundings are transferring heat to the gas, which means the gas is absorbing heat. So, option A should be absorbing heat. Whenever you need to determine whether heat is absorbed or released, it's actually not easy to just figure it out in your head because you're missing a tool, and that tool is the first law of thermodynamics. Never skip the first law, always write out the equation. Alright, so option A is eliminated and we choose C.